ಮ್ಯೂಟ್ ಆಗೈತೆ ನೋಡು, ಅನ್ಮ್ಯೂಟ್ ಮಾಡು.
ಕಾವ್ಯ
ಕಾವ್ಯ ಲಾವಣ್ಯ ಅನ್ಮ್ಯೂಟ್ ಮಾಡು. ಮ್ಯಾಮ್ ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ.
Good morning, ma'am. Today we are going to present the project review presentation of batch 2 on the topic AI powered detection and classification of diabetic retinopathy using deep learning algorithms. The contents are system design and architecture, testing and validation, application and usability. Coming to the system design and architecture, system requirements, the input to our system is the retinal fundus images of patients. Coming to the functional requirements, image processing. First, the system performs pre-processing such as resizing, cropping, normalizing, and enhancing contrast to improve image quality for better accuracy. Next, data augmentation. We use the data augmentation techniques such as rotation, flipping, zooming, brightness adjustments to make the model more robust and prevent overfitting. Deep learning based detection. We use CNN models and transfer learning, particularly DenseNet 169 and AlexNet, to detect and classify the retinal diseases efficiently. Real-time prediction. Finally, the system provides the real-time predictions through the web interface where the users can upload images and get the results instantly. Next, non-functional requirements. Scalability. The system is scalable, meaning it can handle large volumes of medical images from hospitals and diagnostic centers. Easy integration. It is designed for the easy integration into hospital systems so it can be adopted in clinical environments. Next, coming to the hardware requirements. For hardware, we use the Google Colab environment with GPU support, which helps in faster training for deep learning models. Coming to the processor, a system with an Intel Core of i5 or i7 processor or an equivalent one is sufficient to run the project smoothly. Memory, we needed a minimum of 8 GB RAM to handle the large data and keep the learning computations efficiently. Storage, about 10 GB of storage is required for the dataset, trained models, and result files. Coming to the software requirements, operating system used is Windows 10 or 11. Programming language, we use the Python because it has a strong support for the AI and image processing files. Coming to the frameworks and libraries, for deep learning, we use TransferFlow and PyTorch. For machine learning, scikit-learn was used. Data preprocessing and visualization, we use NumPy pandas for data handling and matplotlib and cbin for visualization and results for model performance. Web framework, for deployment, we use the Flask, which helps to create a simple and user-friendly web interface for real-time disease prediction. Coming to the tools, we use a Google Colab for training since it provides the free GPU access and Google Drive to store our datasets and our models. Next will be continued by Meghana.
Next slide. Good morning, everyone. Myself, Meghana. Today, I am here to discuss about architecture. The first step involves data collection, like gathering a comprehensive data set of retinal fundus images. These images can be obtained from Kaggle website, and each image is typically labeled with a grade of diabetic retinopathy, which include no DR, mild DR, severe DR, moderate DR, and a proliferative DR. The second step is a data pre-processing. Like raw medical images may vary in size, quality, and lighting conditions. Pre-processing helps to standardize these images for effective model training, like resizing, normalizing, and enhancing image quality, and remove noise and focus on the retinal area. Resizing means resizing all images to a fixed dimension like 224 into 224 or 512 into 512 pixels. And the third step involves data augmentation. To increase the diversity of the dataset and to reduce the overfitting, augmentation techniques are applied, like rotation at various angles, flipping, zooming, and cropping, translation, etc. Increase the dataset size and model robustness. And the fourth step is a model development. The core of the methodology is designing or selecting an appropriate deep learning architecture, typically a convolutional neural network, due to its excellence in image tasks. Add layers for future extraction and classification. And the fifth step is a training process. The model is trained using the training dataset with labels, use of various validation set to monitor for overfitting and adjust training, monitor validating accuracy to avoid overfitting. Next slide. Sixth step is a model evaluation. After training, the model performance is assessed using accuracy. Accuracy, nothing but overall correctness of predictions and the precision and recall, especially critical in medical diagnosis. And the F1 score, which is a harmonic mean of precision and recall. This helps to identify biases and weaknesses in classification. The seventh step is a system integration. System integration, nothing but the trained model is embedded into a practical system such as a desktop or a web application, and an integration with medical imaging devices, and deploy the model in a desktop or a web app, which allows users to upload images and view DR predictions. Eighth step is a validation and testing. Final model is evaluated on an independent test set that was not seen during training. Real world testing with data from different sources and hospitals. Checking the results with the expert ophthalmologist may validate results for clinical relevance. And the ninth final step is a final DR classification. Like the output is fully trained, validated, and an integrated deep learning model that can detect and classify diabetic retinopathy stages accurately. It serves as a diagnostic aid for ophthalmologists and are potentially be deployed in a telemedicine or rural healthcare setups. Thank you. Next will be continued by Kavya PN.
Good morning, everyone. Myself, Kavya PN, testing and validation, developing and executing test cases to verify the correctness and functionality of the disease detection model across different inputs and scenarios. When we build diabetic retinopathy system, it is not enough to just train the model. We must test it using different conditions that represent the real world scenarios. The goal is to verify correctness of prediction, functionality, and different image qualities, reliability in clinical situation. Test cases design. This table shows five different test cases covering normal, mild, moderate, severe, and proliferative DR, along with low quality images. Each test case has a clearly defined expected behavior. By executing these test cases, we evaluate whether our model can handle real world imaging condition and produce trustworthy result. This process helps in identifying misclassification, robustness issues, and model weakness. Next slide. These are the images. These are the images of the test cases. No DR, mild DR, and moderate severe DR, proliferative DR, low quality image. Next. Validation against expected result to confirm reliability, accuracy, and consistency of models output. Validation methods. Validation methods are used to evaluate whether the diabetic retinopathy detection model performs correctly, reliably, and consistently on unseen data. This ensures the model is suitable for real world use, not just training data. Dataset split. The dataset is divided into three parts: 80% training, used to teach the model how to recognize patterns like hemorrhages, exudates. The model runs features and adjusts internal parameters. 10% for validation, used during training to tune parameters. 10% for testing, completely on unseen data, used only after training is finished. Matrices used. Various performance matrices are used to evaluate classification quality. First one, accuracy, measures how many predictions are correct overall, good for balanced dataset. AUC, area under ROC curve, measures the model's ability to separate the disease versus no disease across different thresholds. Higher AUC means better discrimination power, very important in medical AI. Precision and recall, of all the images predicted as diseased, how many are actually diseased, reduces false positive. F1 score, harmonic balance between precision and recall, especially useful when dataset has a class imbalance. Visualization tools, ROC curve, shows the trade-off between the true positive rate and the false positive rate, helps to compare classifiers. Precision recall curve, useful when some classes are rare, so shows a trade-off between the sensitivity and correctness. Confusion matrix, the table showing the predicted versus actual classes, helps to identify which stages confuses the model. Misclassification patterns, class imbalance issues.
Next. Error analysis and debugging. First one, misclassification review. Analyze wrong prediction to find patterns, reduce missed disease and false alarms. Second one, class-wise performance. Check accuracy for each DR stage. Identify classes that are often confused. Third one, impact of image quality and artifact. Excess blur, glare, and noise effect on prediction. Improve preprocessing for better robustness. Overfitting and underfitting detection. Compare training versus validation performance. Adjust model complexity and regularization. Fifth one, verify dataset imbalance and label noise. Ensure rare classes are properly represented. Reject incorrect or inconsistent labels. These steps help to improve accuracy, reliability, and robustness. Next will be continued by Lavanya.
Good morning, everyone. I am Lavanya GS. Coming to application and usability, the implementation phase of our project where we used a combination of machine learning and web technologies to build a complete working system. Languages are libraries. The backend module is developed using the Python with libraries like TensorFlow, PyTorch, and Scikit-learn, which provide the powerful tools for deep learning and data analysis. Development tool, we deployed the model using the Flask, a lightweight web framework that allowed us to create an easy to use interface for real time predictions. Hardware, for hardware, our system runs efficiently on a regular machine with an Intel i5 processor and 16 GB RAM. The final system allows users to upload images and view the DR stage prediction instantly. Next slide. You, user friendliness and accessibility, we designed the interface to be simple and intuitive so even users with minimal technical knowledge can operate it easily. Clear output display of DR stage, no DR, mild, moderate, severe, and proliferate DR. This makes it suitable for both medical professionals during diagnosis and students or researchers who want to understand the AI based disease detection. Real world applicability. It can be used to automate the DR screening, helping ophthalmologists save time and reduce the manual workload. It is especially useful in rural or under-resourced clinics where eye specialists might not be available. Supports the global health efforts in preventing the diabetes and related blindness. Thank you. Next slide. Thank you, ma'am.
References.
Ma'am,
References.
ma'am,
ಮ್ಯಾಮ್
second ರಿವ್ಯೂಗೆ ಹಾಕಕ್ಕೆ ಹೇಳಿದ್ರು ಮ್ಯಾಮ್.
ಫಸ್ಟ್ ರಿವ್ಯೂ ಅಲ್ಲಿ ಅಕ್ಕ ಕೇಳಿರ್ಲಿಲ್ಲ. ಫಸ್ಟ್ ರಿವ್ಯೂ ಎಲ್ಲ ಹಾಕಿದೀವಿ ಮ್ಯಾಮ್, ಸೆಕೆಂಡ್ ರಿವ್ಯೂ ಅಲ್ಲಿ ಹಾಕಿಲ್ಲ.
Okay. What are the challenges? What are the
Ma'am,
challenges did you face during the model training?
ಮ್ಯಾಮ್
like
ಅಕ್ಯುರೇಸಿ.
Accuracy.
having so much of images may affect the accuracy, ma'am. Like we have taken a 81 GB of data set which contains more than 30,000 images, ma'am. So we can't able to achieve it came 40% of accuracy, ma'am, which we have faced a lot of challenges in it, ma'am. So we are trying to reduce it, ma'am.
Lavanya.
ಮ್ಯಾಮ್ ವಿ ಆರ್ ಫೇಸಿಂಗ್ ಇನ್ ಅಕ್ಯುರೇಸಿ ಮ್ಯಾಮ್. ಲೈಕ್ now we are facing the come 90% accuracy ma'am, but
Yogapriya.
Ma'am, GPU support, ma'am, in all the systems we cannot have the GPU support. We are training in the Google Colab, ma'am. In Google Colab, we have free access to GPU for certain period, ma'am. So that is one of the major challenge in our project, ma'am, we face.
What are the limitations of your project? Kavya.
ಮ್ಯಾಮ್ ಡಾಟಾ ಸೆಟ್ ಇಸ್ ಲಿಮಿಟೆಡ್ ಇದ್ದರೆ ಡಾಟಾ ಸೆಟ್ ಲಿಮಿಟಲ್ಲಿದ್ದರೆ ಟ್ರೈನ್ ಚೆನ್ನಾಗಾಗುತ್ತೆ ಮ್ಯಾಮ್.
Don't use Kannada.
Accuracy. Huh?
Don't use Kannada. Don't use Kannada.
Limited data set can increase accuracy, ma'am.
How does the user interact with your system?
Like we have user-friendly interface, ma'am. Everyone can access it.
Yogapriya?
Through an web interface, ma'am. We have created the web interface, ma'am. Through web interface, they can interact with.
What does the did you use the for your project data set? What data set did you
Aptos
use?
2019, ma'am.
Sorry.
Aptos 2019, ma'am.
Gray image, right?
No, ma'am, color images.
Okay. How many images were used to training and testing?
Like, ma'am, we are working on it, ma'am. We have taken a 81 GB dataset which has more than 30,000 images, ma'am. So we are facing difficulty in training and testing, ma'am. So we are trying to reduce the images, ma'am.
I'm 80%
Like
for
we,
training, 10% for testing, and 10% for validation, ma'am.
80% for
Training, ma'am.
training. Yeah, okay. Testing? 10%.
10%.
10%, ma'am.
What are the convolution layer and pooling layer?
We have to tell. Like we use convolution
Convolutional
layer to, you can tell.
Convolutional layer is a core building block of CNN network. Its job is to extract features like edges, color, shapes, textures, etc. from the input images. Pooling layer comes after the convolutional layer. It reduces the size of the feature map while keeping the important information.
Which algorithm used for detecting?
DenseNet 169 and AlexNet. Ma'am.
Sorry,
DenseNet
Density one.
169 and AlexNet.
Lavanya, explain the working of CNN model.
Ma'am, like methodology is mine, ma'am. So I have taken that part, ma'am.
Yogapriya,
Ma'am, can I explain it?
yeah.
Uh, Go to the methodology slide, Yogopriya. Here in the first step, we gather a comprehensive data set of the retinal fundus images, ma'am. These images can be obtained from Kaggle website, and the each image is labeled with the grade of diabetic retinopathy, like no DR, mild DR, moderate DR, severe DR, and a proliferative DR. And the second step is a data pre-processing. Here we have obtained the data set from the Kaggle website, which may vary in size, quality, and the lighting conditions, ma'am. So pre-processing helps to standardize these images for a effective model training, resizing all images to a fixed dimension. Example 224 into 224 or a 512 into 512 pixels, ma'am. And the third step is a data augmentation. Data augmentation is used to increase the diversity of the data set and to reduce overfitting. Augmentation techniques like a rotation at a various angles or a horizontal or a vertical flipping, zooming, cropping, that type. And the fourth step is a model development. The core of the methodology is designing or selecting an appropriate deep learning model. Here we use a convolutional neural network due to its excellence in image tasks. And the fifth step is a training process. The model is trained using the training dataset with labels. Training is done over multiple epochs, adjusting batch size and learning rate. Epoch nothing but, for example, we consider a batch size of 100 and 1,000 training examples. One epoch nothing but it goes through all the 1,000 training examples all at once. Next slide. And the sixth step is a model evaluation. After training, the model performance is evaluated using accuracy, precision, and recall F1 score. Accuracy nothing but the overall correctness of the predictions, and the precision and recall is especially critical in medical diagnosis. F1 score is a harmonic mean of precision and recall. And the seventh step is a system integration. The model trained is embedded into a practical system like a desktop or a web application, which will be integrated with the medical imaging devices. And the eighth step is a validation and testing. The final model is evaluated on an independent test set that was not seen during training. The real world testing with the data from different hospitals and sources. Like we can contact expert ophthalmologists, which where they can validate results for clinical relevance, ma'am. And the final step is ninth, final DR classification. Once all these steps are done, the output is really fully trained, validated, and integrated deep learning model, which can detect and classify diabetic retinopathy stages accurately, and serves as a diagnostic aid for ophthalmologists, ma'am.
What are the main components of your project for system designing? What are the main component in your system designing?
What are the main components?
Lavanya?
Ma'am,
Like data collection.
input model, pre-processing model, and data augmentation model, feature extraction model, classification model, ma'am.
Yogapriya?
Yes, ma'am. As Lavanya said, these are they are the major factors, and the last one is the evaluation, ma'am. Through F1 score, recall, and precision, these are the major components.
And our system design consists of the several modules, ma'am, starting from data acquisition and pre-processing to feature extraction, classification, and final result display. The CNN model automatically extracts the important retinal features and classifies the image into one of the 5 DR stages, ma'am. Finally, the flash-based interface make it easy for users to upload an image and view the result instantly, ma'am.
Yeah, okay. Thank you.
Thank you, ma'am.
Thank you, ma'am.